CARLA provides realistic physics, divergent maps, and a Python API to control vehicles and access their states, enabling training and generalization across different towns.
Our state vector has 13 dimensions in 3 groups. Lane geometry captures the lateral distance from the lane center and the heading angle, decomposed into sine and cosine to avoid discontinuities when the car turns aggressively. Vehicle dynamics captures the current speed relative to the target speed and the previous steering command, giving the agent memory to smooth its turns. The third group is the most important, a 4-waypoint look ahead. Every tick we sample 4 road center points at 5, 10, 15, and 20 meters ahead and project them into the car's local frame as a lateral and forward offset. On a straight road, all lateral values are 0. On upcoming left turns, they become increasingly negative, and on upcoming right turns, increasingly positive. The action space is fairly straightforward. The agent can only control the steering wheel position and the throttling, both in discrete steps. For each steering wheel position, hard left, straight, gentle right, and hard right, the agent can also configure a light throttle or a full throttle, thus defining the 10 discrete actions.
For the reward, at each time step, the reward is speed minus penalty. We encourage good speed and penalize line deviation, heading error, and going offline. The weights are chosen empirically.
The training of our network consisted into 2 phases. Phase 1 consists of collecting a lot of data from an expert controller, and Phase 2 consists of offline training. To generate training data, we ran hundreds of episodes using a rule-based expert controller, inspired by the Stanley controller from Stanford's DARPA Grand Challenge. To ensure the data covers a wide range of driving situations, we add Gaussian noise to the steering decisions, vary the target speed across episodes, and periodically inject deliberate perturbations that push the car off-center so the expert demonstrates recovery. Without this diversity, the training agent gets stuck whenever it drifts into states that it never really visited, something we observed repeatedly in early experiments. The agent is a dueling deep Q network. It is trained offline on the gathered data from the expert and disturbed Stanley controller. The shown image has the details of the implementation. The original attempt was to build a simple DQN with multilayer perception that takes in as an input the 13-dimension state vector and outputs an action, the argmax of the output layer of dimension 10. However, the agent's performance was poor, and it often got stuck on curves. The first step towards diminishing this problem was employing a dueling DQN. This architecture is similar to an MLP, but after a number of hidden layers, it splits into 2 branches, namely a value stream and an advantage stream. The Q value is then computed based on this equation, where V of S is the value stream, A of S and A is the advantage stream, and mu is the mean advantage. This ensures that the agent can separate the value of each state and the advantage of each action. The main advantage of a dueling DQN is that it helps address the issue of separating the value of a state and the advantage of the next action. The goal of training is to approximate the Q function, a function that tells us the expected total future reward of taking a given action in a given state. We use the Bellman equation, which states that the Q value of a state action pair equals the immediate reward plus the discounted value of the best action in the next state. This recursive definition is what lets us learn Q from data. The training loop is straightforward. We sample a batch of transitions from our expert dataset, compute what the network currently predicts for each state action pair, compute a target using the Bellman equation, and minimize the mean squared error between the two. A key detail is that we use a separate target network, which is a frozen copy of the DQN that only syncs every 1,000 steps to keep the training targets stable. Without this, the targets would shift with every gradient update, creating a moving target problem that destabilizes learning.
So for the network evaluation, our best agent was trained on towns 1, 2, and 3 and achieved positive average rewards in the thousands on all 3, a significant improvement over earlier iterations that would get stuck on curves and accumulate large negative rewards. It completes 3,000 episodes with 0 line departures on the training towns, handles left and right turns smoothly and maintains speed near the target rather than crawling. More importantly, it generalized. On towns 4 and 5, the agent has never seen their training. It still averages rewards in thousands, maintaining good speed, and only very rarely departs the line. The driving is not perfect. There are some oscillation on long straight roads and occasional hesitation in turning sharp curves, but the agent is clearly driving, not stuck, across 5 different towns with different road geometries.